Today we are back and we're going to do the second part of the history of the atoms notes. If you remember yesterday, we started with a model and talking about how all models fall short of reality, but we use models to try to explain things that are too big or too small to work with. Then we went through and talked about Democritus, and he was the first person to theorize that everything is made of these indivisible atoms. If you keep cutting something down, you'll eventually hit something that you can't divide anymore. He called them atomos, which means indivisible. And then he kind of wasn't accepted with his theory because he had no proof. And at the current day in Greek times, people thought that everything was made of earth, wind, fire, and water. Then fast forward 2,000 years, we had two people that found pieces of evidence of atoms, and the first one was Lavoisier. Lavoisier was doing his work with different reactions in closed containers and wrote the law of conservation of mass, which started to support the idea that everything must have been made of atoms. After Lavoisier, we had Proust, who wrote the law of definite proportions, because every time he pulled apart water, he got 2 hydrogens and 1 oxygen. Then we moved on to Dalton, who kind of took everything everybody was saying and wrote Dalton's atomic theory, where he said, number 1, that all matter is made of atoms that are indivisible and indestructible. Number 2, atoms of the same element are the same. Number 3, atoms of different elements are different. And then number 4, compounds are made of atoms in a definite proportion. And then he was, as you can see, they said, what do you think an atom looks like? And he simply said a marble. He thought they were indivisible little spheres that could not be broken down any further. So today we're going to talk about 2 more scientists who are going to extend our knowledge of the atom and find some of the subatomic particles that we have already been talking about in class. Okay. So the first person we're going to talk about here, and I would write these down in your notes, right under the notes from yesterday. You don't even need to re-head it up if you want to just continue a list. The first person we're going to talk about today is J.J. Thomson. He was working in the late 1800s, and what he did was he found a negative part of the atom. And so what he discovered was the electron. He used a cathode ray tube, which we don't have any of those, but I have a short little clip to kind of show you what happened. But the idea is that he was streaming pieces of an atom that he found, and then he would find that they were attracted to a positive side and they were repelled by a negative side. And if you know opposites attract, likes repel, he found that these things must have a negative charge.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the 2 metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons.
All right, so kind of in that short little clip, you can kind of see how it worked. And the idea is that we must have found these electrons as they were being attracted to the positive plate. There is also a cathode ray, an actual one here that you can see. What you see is a stream of actual negative particles, which we know is electricity now. So we have your electrons coming through, and they are repelled by the negative side because likes repel. And then if they were to switch the magnet around, it would be attracted to the positive side.
This is a demonstration of
heavens, we don't need that business. Get out of here. Thank you, cathode ray tube. So he found a part of the atom. So we know that Dalton is not correct. It's not an indivisible and indestructible little marble. And so they asked J.J. Thomson, what do you think? What does an atom look like? And I don't know what he was thinking, but apparently he liked dessert. So usually people find things in their everyday life that they would then try to mimic when they're coming up with answers. So what you see here is what they call plum pudding. It was a dessert at the time. It doesn't sound appetizing to me. I would liken it more to like chocolate chip ice cream. There were negative plums, okay, like chocolate chips, or maybe like a chocolate chip cake or something like that, and he thought that the pudding or the cake around it must have been positive. So when he looked at plum pudding, he said, maybe an atom looks like that. So the idea, what I would kind of draw in my notes, is the idea that he had, and I would write this down, the plum pudding model. And in his plum pudding model, the pudding portion, which I learned is more like cake, not like pudding, but that's okay. The pudding is a positive medium. And in there, he must have thought little negative electrons kind of reside. Okay, and you can kind of see in this picture down here. He was smart enough to know if I have a negative part, I must also have a positive part because these overall have to be neutral. So he had the plum pudding model where the negative electrons are kind of scattered throughout this positively charged medium. Okay. And as science goes, as soon as you think that you have a discovery in a model, somebody's going to come along and try to debunk it to make sure that it's true. And so for the last scientist today, that is what he did. Basically, what he did is he fired a gun at this plum pudding to try to see if he could hit something or if it would go straight through. And if Thomson was correct, these bullets should whiz right through this and not hit anything. So the next person that you saw, and you might have heard of him, he is one of the most famous history of the atom scientists. His name is Ernest Rutherford. He was working in the early 1900s, Rutherford, and he did what's called the gold foil experiment. And what he was doing is he was trying to support or discredit what Thomson was working on. And so he set up a little emitter for an alpha particle, and alpha means positive. So this little beam of particles was going to shoot right through a very thin piece of gold foil. Okay. And what they were hoping to see is that if Thomson was correct, the expected results were that these little particles, these little alpha positive particles here, should fire right through and not hit anything. Okay? And I have a little historical reenactment of what actually happened with his experiment. The guy has a little bit of an accent, so hopefully you can understand him. We'll talk about what he said here in a minute.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position, behind the foil, it will measure 1 count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics.
So to break down what he just said was these alpha particles went straight, or they thought were going to go straight through, but they actually hit something, okay? And what they were hitting was the nucleus of the atom. So the actual results that they got were not what they expected. And these particles would go through, most of them would go through, but all of a sudden something hit something and they were deflected. So what he actually found, his conclusion, and I would jot this down, the conclusion of the gold foil experiment by Rutherford was that they located the nucleus of the atom. From this experiment, they concluded 3 things, and they made a new model. The 3 things about the atom is the first thing is that they missed, and like he said, you have thousands and thousands that go straight through. So they must have had an extremely small, very, very small nucleus, because most of the time you were missing, okay? Think about if you're doing target practice, the smaller the target, the more likely you are to miss. The other thing about the nucleus is that if we were firing positive particles at it, and it was, over here, positive particles, and they were being deflected, that means it had to be the same charge. The nucleus must have been positively charged, basically where it was locating the protons. And the last thing that he said about the nucleus is because it could basically stop a speeding bullet. Okay, I mean, you were like stopping the firing of these alpha particles. It must be extremely massive. Now, massive is a hard word. Sometimes massive people think are big. It's very small in size, but it has all the mass of the atom. And you guys know that because of your calculations last week. There is no mass, or relatively none, of the electrons outside the nucleus. All the protons and neutrons now we know are in the nucleus. So all of the mass resides in the nucleus. So they said, all right, plum pudding's out. What do you think? And so what he said is, I don't know a lot about the atom, but I do know there's a nucleus, and I know that there's a lot of empty space. So our next model of the atom is that most of the atom is empty space, and this would be the new, oh, that's way too big. That would be the dense, small, positively charged nucleus, and everything else around is empty space. They say, if you would like to know, if you take the end of a pen, and you hold this on the 50-yard line of the football field out in the back, that would be the size of the nucleus, and the first electrons would be on the track running around the actual football itself. So we're talking about an extremely small nucleus versus the large size of the atom. So most of the atom, and it's very crazy to think about, most of the atoms that make up our everything are nothing but a nucleus and some electrons in empty space. Okay, so hopefully we're making some more progress in our understanding of the atom. Don't forget to do your lecture questions here, and we will pick this up and even further our understanding of the atom when we come back on Monday.